Hello everybody, and welcome to Learning Target 2.3 in the ecology unit, limiting factors and carrying capacity. And before we begin, I want you to take a look at these two images right here. Which fish would you rather be? Would you rather be these guys, right here, or these guys? Well, you probably answered these guys. They look happy. And that's because they have a lot less of certain things, a lot more of other things. So take a minute and just pause the video and think about what are some things that these fish have that these ones don't, besides the obvious things. Let's continue. So just to get the definition out of the way, and this is part one of the video here, a limiting factor is something that causes population growth to decrease. So if you're in the environment, if you can think of anything that might cause a population of organisms to go down, to decrease, that would be a limiting factor. Oxygen, water, space, soil, air, access to food, competition. Anything that would cause a population to decrease could be considered a limiting factor. Now there's two types of limiting factors that we need to be familiar with. The first type is called density-dependent limiting factors. And in this case, size of a population does matter. When we get starting larger populations, when there's large populations, like you saw in that fishbowl there, we get into trouble because limiting factors start to cause problems. Things start running out. So as you can imagine, as a large population gets larger, there's increased competition. There's more predation. You might be more susceptible to diseases and parasites if you live in large populations. So that's density-dependent limiting factors. Density-independent limiting factors, on the other hand, are caused when they don't really care about the population size. Population size doesn't matter. And in this instance, we can talk about drought and other climate extremes, as well as human disturbances. We'll get more into these in a bit. Sorry about that. Moving on. So let's focus now on some examples of density-dependent limiting factors. The first example here is competition. Now, my image kind of blocks this, but there's a lot of deer in this picture. And when there's a large population, populations become crowded. And there's increased competition. So they're competing for food, for space, for mates, for resources, for shelter. Deer is a great example because the deer population, especially around the Northeast and in places like Long Island, and even parts of New York City, believe it or not, are being inundated with deer because there's no predators there to reduce the population. So the deer population is really out of control in some places, and this causes some problems that we'll talk about later on in the video. Second example of a density-dependent limiting factor are predators. We learned about predators in the last learning target. Well, predators are also something that can decrease the size of a population. Here's a lynx and a hare, or predator-prey interaction. So we take a look at this graph again. In this instance, the hare's population is limited by the size of the lynx population. So as the lynx population goes up, the hare population goes down. But at the same time, the lynx population is also limited by the size of the hare population. So when that hare population drops, well, a little bit later, so does the lynx population. So the predator and the prey are kind of dependent upon one another. The third example of a density-dependent factor, or limiting factor, is parasitism and disease. Parasitism was another one of the terms of a symbiotic relationship from the last learning target. And if you look at this little moth right here, it's being parasitized by all these different wasp eggs. So what happens is a wasp comes and lays eggs, and this poor moth has to carry them around. When these eggs hatch, believe it or not, they actually eat this moth right here. But anyways, the reason why parasitism and disease are a limiting factor is because populations get larger and more people are in one space, or more organisms, I should say, are in one space. they can run into trouble with having increased parasitism and increased chances of spreading diseases. So that's density-dependent limiting factors. Now let's talk about density-independent limiting factors. And just to refresh our memory, density-independent limiting factors are when population sizes do not matter. The population size can be huge, or the population size can be medium, or even little teeny tiny population size. It doesn't matter how big the population size is for density-independent limiting factors, because they affect all populations the same. In one example, this could be drought. Right? If you're a large population, if you're a small population, if there's no rain, there's no water, everybody's going to be affected equally. Same thing if it gets super, super cold outside, like it did last winter for a lot of organisms. They had a hard time surviving, regardless of the size of the population. A flood that comes in all of a sudden, or a hurricane, that's a density-independent limiting factor. It doesn't matter how large the population is, it can affect everybody the same. The same thing is true on a really, really hot day. You could be one person or one organism in the middle of an area and be really, really hot, and you could be hundreds of organisms in one area and be really, really hot. It doesn't matter because it's density independent. Here's another example. Humans, us, me, and you. We are density independent limiting factors. Unfortunately, humans are really, really good at destroying natural things. Take a look at this picture up here. Deforestation, for example, cutting down lots of trees. Pollution, it affects everyone more or less equally. Hunting, people have done a really, unfortunately, bad job of conserving populations. So hunting is another thing that can cause a population to go down. Again, a limiting factor in anything that causes a population to decline. Humans, we've done that. People say that right now the Earth is experiencing its 6th mass extinction, mainly because of human actions. More organisms are going extinct now and at a faster rate than any ever other time before in the history of Earth. And Earth's really old, 4.5 billion years old. It's only in the last few hundred years that we've really, as humans, caused these major destructive impacts on our environment. We'll talk more about human population growth and connect it to limiting factors in the next few slides, towards the back of this video. Let's check in with yourselves, all right? You should pause the video right now and check yourself and make sure you know what a limiting factor is. You remember to take a note down and write down that definition. Also, can you tell me the difference between a density-dependent and a density-independent limiting factor? And then can you provide examples of the density-dependent limiting factors that I just went over with you, as well as 2 examples of the density-independent limiting factors? All right, part 2, carrying capacity. Carrying capacity is all about this graph right here. And also, carrying capacity is all about the maximum population size that any given area can support. So if you think about an ecosystem, or you think about a park, if you think about a forest, there's only enough resources in that particular area to support a certain number of organisms. Any more organisms than there are resources, then you run into trouble with survival rates. So if we look at this graph, for example, we can see the carrying capacity being represented in this blue line, this horizontal line as a carrying capacity. Sometimes you see the word carrying capacity actually in an elevator or a room. I'll say the carrying capacity in this elevator is 2,000 pounds. That's the maximum amount of weight you want to put in that elevator. More than 2,000 pounds, watch out. You might not have a very nice ride on that elevator. Okay? Same thing is true in the real world of organisms in an environment. Populations, when there's not a lot of individual organisms in the population, things are okay. There's enough resources, there's enough food, there's enough water, there's enough shelter, there's enough oxygen, there's enough soil, there's enough places to hide. But as the populations grow, competition starts to cause problems for individual organisms. So as a result, when we get to more and more increases in the population, sometimes populations overshoot or go over the carrying capacity. When this happens, what typically occurs is a drop, a rapid drop in the population size. Now, the population size doesn't typically drop all the way back down, although sometimes that is the case. It typically kind of goes down, and then when there's enough resources again, it shoots back up. And it goes down, and it shoots back up. It's kind of like this balancing act. Sometimes you may have heard it as called dynamic equilibrium. This idea of the ecosystem staying in this steady, balanced state around this carrying capacity, making sure that there's enough resources, and if there are, the population will increase. But if competition for those resources becomes too great, you'll see the population go down. Okay, now let's start putting our two topics together, carrying capacity and limiting factors. I can explain this through this story about reindeer. So let's imagine it was the year 1911 and there's an island. And on this island, 25 reindeer were introduced to the island. And guess what? There's no other reindeer on that island. There's plenty of food to eat, and there's plenty of space, and there's not a lot of predators. There's actually no predators whatsoever. Reindeer are very, very happy on this island, aren't they? So what happens? They reproduce, and they don't die that often. So look, in the next 15, 20 years, the population of these reindeer starts to increase, and then boom, the population rapidly increases from about 25 to 2,000 in 20 years. That is a problem because all of a sudden, now there's no food. Now maybe there's a temperature swing. Now the range where they eat is depleted. Grass can't grow fast enough. As a result, you have all these reindeer starving. So this is an extreme example of carrying capacity and what can happen when limiting factors and resources run out. It doesn't exactly show the balanced dynamic equilibrium that we talked about in the previous slide, but it just proves the point that when you have a population that runs out of resources, that has these limiting factors, their population crashes because that population has exceeded its carrying capacity, or the maximum number of organisms that a given area can support. All right, now let's connect this to us, humans. We're kind of unique organisms. We're not really considered to be animals, even though we are animals. We're kind of outside of the rules of nature and ecology. But let's look at what's going on in the human population over the last 2,000 years, just as an interesting example to connect it to carrying capacity. So look, way back in the day when my man Jesus Christ was born in the year 0, right? Look, there was only about 500,000 people, 500 million people on Earth, right? Not even a million, not even a billion people, maybe not even half a billion people. And that stayed more or less the same for, I don't know, 1,800 years. Not until the year 1800, 1,800 years after Jesus was born, that the human population hits 1 billion. And then what happens? Well, during that time, it's industrialization. More people are moving to cities, and the population starts to increase. And then, boom! In the last 150 years, the population of humans has rapidly increased. It took 1,800 years to go to 1 billion. It only took about another 100 or so years to double to 2 billion. And once we got to 2 billion, we hit 3 billion, and 4 billion, and 5 billion, and 6 billion, and now the human population is over 7 billion people on Earth. Now this dotted line right here is what some people expect to be Earth's carrying capacity, or the human population carrying capacity. And as you can see, the human population is well over that carrying capacity. Now, we don't know, is the human population going to crash? Or, as some people think, are we going to come up with new technologies and new resources to make sure that this human population growth is sustainable? To be determined. All right, last slide here. Let's carrying capacity in the reading exam, or your upcoming test, or your vocabulary, or no, sorry, your verbal quiz. Sometimes on the Regents, they may ask you what certain letters mean. For example, they may ask you which line indicates the carrying capacity. Well, you should know it's the dotted line, the one that's horizontal. That represents the carrying capacity of any given population. And here it happens to be 500. Also, sometimes they might ask, at what part of the graph is the population increasing the most rapidly? And to answer that, you need to look at what part of the graph has the greatest or most steep slope. And that's right here. When it's going from 5 generations to 10 generations, the population is increasing very rapidly because there's this steep incline, or let's say it looks like that on the graph, from A to B. All right, so that's carrying capacity, that's limiting factors. You should be able to answer some of these questions by the end of the slideshow, and I'm looking forward to talking to you some more after you do the activity and come and see me and take the verbal quiz. Don't worry about this slide, that was just in there as a bonus. Stick on that one.